And of course, many people have contributed, and many people have contributed much more than I did to this design. So this is the first design report that was ready for printing. It's volume 2 of the CDR, and as the other volumes do, it has more than 1,300 contributors from 350 institutes. So it's difficult to give credit to all of them, but I try to mention the colleagues who have made important contribution to the accelerator design. This is not yet arrived. I'm told it's in the post. If you are lucky, the volume will be here this evening. Basic design choices are summarized on this slide. The FCC-ee is a double ring collider. Of course, has a circumference of about 100 kilometers. It follows the footprint of the Hadron Collider, FCC-HH, except around the interaction points, where we have, as already mentioned by Michael Benedict this morning, where we have an asymmetric IR layout and optics to limit the synchrotron radiation emitted towards the detector. And also this asymmetry also allows to separate the booster. We want to have top-up injection and inject at full energy into this machine. So we need a booster synchrotron in the same, a rapidly cycling booster in the same machine, in the same tunnel. And it's separated by about 10.5 meters from the collision point, which is large enough to fit the detector in between. So this solves asymmetric layout, also solves the problem of separating the booster synchrotron and the collider around the detector. Oops, my God. What is this? Okay, presently we have 2 interaction points at the same location as the main experiment as the Hadron Collider, and alternative layouts with 3 or 4 IPs are under study. We have a large horizontal crossing angle, 30 milliradian, and we use a so-called Krebs-Waist optics to get the maximum luminosity and allow for a very small vertical beta star. Synchrotron radiation power has been limited to 50 megawatt per beam at all beam energies. This is a design input that we have put that determines the maximum current at all energies. And per unit length, the synchrotron radiation power is about the same radiation as we had in lab. And we taper all the arc magnets to match the local energy. This we can do with a double ring collider. It was not possible with a single ring collider. So we don't have any orbit offsets due to the synchrotron radiation. And I already mentioned we have this top-up scheme which can sustain a very short beam lifetime due to the very high luminosity, and this requires this booster and the top-up booster in the same time. Okay, these are the parameters we want to run mainly at 4 operation points. At the Z pole, we have a beam current of around 1.4 amps, which is similar to the B factories, KKB and PEP2, or Daphne. And then we run at the WW, at the Higgs, and at the TT bar. At the TT bar, the beam current goes down to a few milliamps, which is very similar to Lab 2. So we changed, you can see here the bunch intensity is more or less the same at the different working points. It's around 2×10⁻11 per bunch. And we just vary the number of bunches as we go up in energy for these different working points. Synchrotron radiation energy loss per turn is very low at the Z, only 36 MeV per turn. We need an RF voltage around 100 megavolt to compensate. And at the TT bar, we lose around 9 GeV per turn. And we need an RF voltage around 11 gigavolt. For comparison, lab had the energy loss around 3.5 GeV at the highest energy. You can see the radiation damping time correspondingly becomes rather short. At the TT bar, we have 20 turns radiation damping time longitudinally, which is very good. This allows for higher beam-beam tune shift. Then high luminosity is achieved by very small beta star. Beta star vertically is around 1 millimeter, and lab had 40 or 50 millimeters. So we gain a huge factor in luminosity also through this very small beta star. Emittances are naturally very small for the very large ring because we have a small dispersion. You can see here the numbers around 1 nanometer in the horizontal plane and around a picometer or 1 or 2 picometers vertically. And we have a rather large effect of beamstrahlung. Synchrotron radiation in the field of the other beam gives rise to a large quantum fluctuation, multi-turn quantum fluctuation. So actually the natural natural bunch length without collision, for example, at the Z is 3.5 millimeter. If we collide the beams, this bunch length increases a factor 3 to 4 to 12 millimeter due to the beamstrahlung, the synchrotron radiation in the field of the other beam. This effect becomes less pronounced at higher energy. At the TT bar, the effect of Beamstrahlung to the bunch length is more benign, also thanks to the much stronger radiation damping. Luminosities per IP are indicated here. We have more than 10 to the 36 per IP at the Z, and this goes down to around more than 1.5 times 34 per IP at the TT bar. Here's the beam lifetime is unavoidably limited by radiative Barber scattering and the luminosity and the beam current. So at the Z, beam lifetime is more than 1 hour, also at the W around 1 hour, and then it goes down to around 20 minutes here at the Higgs, and at the TT bar energies we have a new effect. We have also an particle loss due to the emission of Beamstrahlung photons with rather high energy, so that the emitting particle falls out of the momentum acceptance of the machine. So there we limited by design this Beamstrahlung beam lifetime to around 20 minutes. This is still rather comfortable. The super KEKB is designed with a beam lifetime of 5 minutes and a simulated lifetime of 2.5 minutes. So here we have a factor 10 longer beam lifetime. This shows the luminosity on a linear log scale. So the luminosity is shown logarithmically. Here is the total luminosity for 2 IPs. We are around 4 times 36, and it goes down like this. This goes like not like 1 over the force, no, sorry, not like the force minus force power, but minus 3.5 power roughly. We go down. And we have another operation mode, which is not the baseline, but we could also try to produce a Higgs in the S channel at 125 GeV center of mass, where luminosity would be somewhat lower, but we could do this with a monochromatization to have an energy spread comparable to the width of the Higgs, to measure the U-Carver coupling to the E plus E minus. Okay, this shows a plot presented this morning by Michael, luminosity versus energy on a log scale now. You see the glorious history of colliders, more than 50 years, maybe 70 years of E plus E minus colliders, starting in Frascati and in France, and then Novosibirsk, etc. In the last 20 years, we had still LEP at very high energy, which defined the energy frontier so far, and then we had the PEP2 and KEKB, which set a new level of luminosity for E plus E minus colliders. Super KEKB is under commissioning. It aims for 50 times higher luminosity than KEKB. And also there are 2 proposals for tau charm factories, which use similar ingredients and also aim for very high luminosity. Michael already presented this morning the list of new ingredients that we can copy and include from these different machines. They have taught us different lessons. High energy operation with very high photon energies we learned at lab. Double ring, all of these new machines are double ring colliders, which allows for much higher beam current. And we have top-up injection already demonstrated in KEKB and PEP2. Daphne showed the successfully Krebs operation. And super KEKB will go to very low vertical beta star, 10 times lower than what we plan, almost 10, no, maybe 5 times lower than what we planned for the FCC-ee. Also, we want a very precise energy calibration. This has been pioneered at Web4M and at Lab. And we have, as you will see later, we have a positron source which is similar to what is being done for KEKB and super KEKB. So this is, combining these new ingredients allows us to make another step forward or 2 steps forward in luminosity and energy. This is the final focus optics. It's a very novel design. It's asymmetric. And because we want to limit the incoming synchronization, we have very weak bending. As you saw already in the geometry, these bending magnets are extremely weak. And then on the outgoing side, you have stronger magnets, and you have a closer spacing, and then you have more magnets, which brings the beam back onto the footprint of the hadron machine. There's a local chromatic correction. As you can see here in the middle, the collision point, and the peaks in the final doublet. And then you have locations where we put sextuplets. We have a local vertical chromatic correction. So the sextuplets at point B and C corrects the chromaticity of the final doublet. And then we have additional sextuplets A and D, which in principle cancel the geometric aberration of these chromatic sextuplets. But if we reduce the strength, we get the Krebs vase. So actually, we get the Krebs vase with a minimum amount of nonlinearity, which is developed by Katsunobu-Ueda. This is called a virtual Krebs vase. So with basically 2 sextuplets only, we get the chromatic correction and the Krebs vase. Okay, and we have, over the last 450 meters from the collision point, we have less than 100 keV critical photo energy. This is a lesson, one of the lessons learned by lab in order to minimize the detector background. Okay. Okay, and at the very IP we have novel, at the moment we are studying novel advanced final focus magnets based on canted cosine theta technology. So there's some synergy with the FCC-ee program perhaps. The strongest magnet in the machine is actually the final focus sextupole because it's very short to minimize aberrations and it has a high peak field of around 10 to 11 Tesla at the moment, which could be perhaps built based on HTS wires. There will be. And then we have a similar technology for the final quadrupole pair near the IP. Same type of technology. Oops, again lost. Same type of technology, but this could be could be based on nylon titanium, and we can include in this canted cosine theta magnet also correction coils to minimize the effect of one magnet on the other beam. Anyway, I think there are some talks about this by Mike Horazinus at this workshop. Okay, interaction region looks like this. Different critical elements are indicated here. We have a central chamber which is slightly smaller in diameter than the incoming beam pipes. This is to minimize higher order modes and try to avoid as much as possible higher order modes and trap modes generated in this part of the interaction region. And in addition, some unavoidable higher order modes, they are damped with a higher order mode absorber located at this Y, at this crotch chamber. And then we have luminosity monitor somewhere here. And we have mass to minimize, again, incoming reflected photons hitting the inner beam pipe. We have rather complicated magnet system. We have the detector solenoid, and then there is a compensation solenoid. Sorry, this is luminometer. There's a compensation solenoid followed by the first quadrupole, which is surrounded by a shielding solenoid. So there's a rather complex system of solenoids around this collision point. And the fringe field of the solenoids gives also some contribution to the vertical emittance of the machine. And the correct modeling is difficult, but it's important to get the expected performance. We have different arc optics. Now to come to the arcs of the collider, we have the same magnets, but we power them differently. At the Z and W, we want to increase the emittance, or we want a rather large emittance if possible. And we use the 60-degree optics. The chromatic correction is always done with sextupole pairs, which are separated by -I transform. So one of these pairs can be excited without generating any other low-order aberrations. And then if we go up in energy to the Higgs or TT bar production, we go to a 90-degree phase advance optics, and that means we need the different sextupole pairs. We need other sextupole, additional sextupoles, and different pairs to make a -I transform. This is indicated here. So at the high energy, we have about 600 independent sextupole pairs, and at the W and Z 400. And each individual pair, the strength of all these pairs is optimized by Katsunobu Ide to get the maximum dynamic aperture and maximum off-energy dynamic aperture. The result looks like this for the different energies. On the horizontal axis, you have the energy offset, and vertically, you have a horizontal transverse acceptance. So we have at the Z, we have plus minus 1.3%, and the most critical is a high energy off moment on aperture at the Higgs and at the TT bar, where we are limited by this Beamstrahlung lifetime effect. And there at the TT bar, we have minus 2.8%, plus 2.4%, and this sets the lifetime of our beam. It's a rather remarkable achievement. I remember when we started the study 6 years ago, we had a quarter of a sigma dynamic aperture before Katsunobu arrived at that. So this is a dramatic improvement. Okay, we study the vertical emittance is important for the luminosity. So we try to do studies with realistic errors. This is one of the latest sets. We have 100 micron misalignments for the R quadrupoles, IP quadrupoles, sextupoles, dipoles, and 20 micron misalignment, random misalignment between the BPMs and the quadrupoles. This is quite realistic. And after iterative optics correction, Tessa, Charles, and colleagues, they get this type of performance. We get an RMS vertical emittance over many seats of about 0.12 picometer, and our target value is 2.9 picometer. So there is a huge margin. However, we need such margin because things get worse if we don't believe this analytical emittance calculation, but do particle tracking. We see actually that just doing a tracking in the lattice with nonlinearities, etc., we get, instead of 0.08 picometer, we get 0.3 picometer, on the factor 3 or 4 increase. And if we also include beam-beam collisions, the beam blows up more, and we come to 0.8 picometer in collision. This is still smaller than the 2 picometer target, but it's much larger than the bare emittance that we get from MedX. So this looks good, but there's also interesting physics here. And some possible explanation is in this old paper from Uide-san and Koiso-san. Anyway, good news is target emittance is achieved with realistic errors and including beam-beam. For energy calibration at the Z and W threshold, we want to use resonant depolarization. This has been studied in quite some detail over many years by Iliana Gianfelice. She uses the old software tools that were developed for Hera. And she also performs orbit corrections, optics correction, and then she does some harmonic spin matching. And she gets rather high, very high polarization levels at equilibrium self-polarization levels at the Z, more than 80%. And also at the W, she can achieve more than 30 or 40%. Now, one problem at the Z is that the polarization time is quite long, so we want to use additional wigglers, 8 asymmetric wigglers, to shorten the polarization time. And this we would do with some pilot bunches. The idea is to have 200 non-colliding pilot bunches which are injected with wigglers on, which get polarized quickly. And then these pilot bunches individually can be depolarized to determine the energy later in the store. Another feature of our design is we locate the RF in the Z running, maybe also in the W running. We locate the RF section in one point of the machine. This avoids a large systematic error in the energy calibration. Anyway, this depolarization technique was, of course, used routinely for the Z running at lab. So the forecast is that the luminosity average center of mass uncertainty is about 100 keV at the Z pole and about 300 keV at the W threshold. And these values are important for the physics program. Actually, for this, there's also a nice summary in the physical review exercise and beams describing the polarization calculation. So we can get the energy caliber at the 10 to minus 6 level. For higher energies, this is no longer possible because we lose polarization if the energy spread gets too high at the Higgs and at the TT bar. We can use this. We can use a Compton polarimeter. We can use a Compton polarimeter to measure the recoil of the photons and get another estimate of the energy at the 10 to minus 5 level instead of 10 to minus 6. This technique is being used at Novosibirsk. And this would give us an uncertainty of the order of a few MeV in the center of mass energy for the Higgs and TT bar. But by the way, the nice feature is that we can use the same hardware as the polarimeter hardware also to do this type of energy calibration measurement. In addition to the center of mass energy, also the energy spread is an issue. So there is a study, the proposal that we can use the muon pairs, 10 to the 6 muon pairs are produced every 5 minutes at the Z, and this can be used to measure the beam energy spread. Now I come to the injector complex. This is a sketch. We have a LINAC. In the baseline, we have a SLC or super KKB-like S-band LINAC, 6 GV LINAC, which excites 1 or 2 bunches at 100 Hz or 200 Hz. And then the same LINAC can be used for positron production, and we put a positron target at 4.5 GeV. Then we can produce positrons, accelerate in the rest of the LINAC to 1.5 GeV, which is the energy of a damping ring. For the positrons, we need a damping ring to reduce the emittance because it's large after the target. In the baseline, we inject at 6 GeV then into a pre-booster ring, which could be the SPS, as it was the case for lab. And then from the pre-booster, we inject into the top-up booster. We are studying now alternatives. Instead of a 6 GeV LINAC, we could put a 20 GeV LINAC and avoid the pre-booster, for example. We should make a comparison of performance and cost. The machine parameters are such that we can fill the machine from 0 in 20 minutes and that we can easily do the continuous top-up. The positron rate that we need is indicated here. This is a comparison. You see the routinely achieved for SLC had this rate, super KKB at the moment achieves this, and this is the design value for super KKB. Required for top-up are these values here, and FCC, the most demanding case is the Z, but the number of positrons per second that we need is much, much less than what was produced at the SLC and what is being produced for super KKB right now. It's also shown in this lower table. we need less than 10 to the 12 positrons per second at the Z, and SLC had 6 10 to the 12. So linear colliders need a lot more. We have a preliminary design of this positron source flux concentrator from Nobel Beers, and the LAL team is working on simulation optimizing of the positron source. I come to the operation model. We have the 4 different energies, so and these are the target physics goals defined by the experiment, by the physicists. So we want to have 150 inverse autobahn at the Z, 10 inverse autobahn at W, 5 inverse autobahn at the Higgs, and then 1.5 or 1.7 inverse autobahn at the top here. And this is the assumed typical luminosity. We take a value which is 10 or 15% lower than the design value. And then we assume also that in the first 2 years we get only half of this value. And then we have a model which gives us, I'll show you on the next slide, then we have a model which from this typical luminosity we get to integrate luminosity per year. We get these values, and that makes a runtime of 4 years on the Z, 1 or 2 years on the W, 3 years on the Higgs. Then we need 1 year shutdown to install additional RF and reconfigure the RF for the top running, and then we run another 5 years on the top. So a total operation program is 15 years. Oops. Okay, the integrated luminosity per year is calculated like this. We take this nominal luminosity, which is already 10 or 15% lower. We multiply with the number of physics days and with the efficiency. So the number of physics days, we assume 185 days, and efficiency, we assume 75%, including top-up. And this efficiency value is based on operational experience at different machines, including top-up. And effectively, if you take the design luminosity and ask what is the effective number of seconds per year we use for this luminosity estimate, it's around 10 to the 7 seconds per year, which is lower than for many of the competing proposals. The T is computed like this. We have 365 days in the year. We take 17 weeks of winter shutdown. This is 2 times longer than the estimated minimum required for the RF changes. We subtract also 30 days of commissioning every year. We subtract 20 days for machine development, plus 11 days for technical stops. We end up with 185 days. For the efficiency, these are historical plots from John Zimmermann from PEP2 with top-up injection. Here's an example from 2004. From 2008, you see the beam currents and the luminosity. And most of the time, beam current is constant and luminosity is almost constant, except if there is a failure, you need some time to recover. So similar plots we have from KKB. Oh, okay. Then I come to the RF. The most important technology of the lepton collider is the RF system. And as I told you, at the Z, we have very high beam current and low voltage. At the TT bar, we have a high voltage but very low current. So we need a different RF system to get the optimum performance. In the first stage, we have single cell, 400 megahertz cavities, niobium on copper. Then for the W Higgs and top, we replace these cavities with 4-cell cavities, and for the TT bar, we also add 800 megahertz bulk niobium cavities. So this is a schedule defined by the RF group. You can see the number of cryo modules which have to be installed in the different shutdowns and which have to be taken out of these different types of cavities. So this has been defined, and it fits well into the schedule that I presented earlier. We have 400 megahertz cavities at CERN. Of course, LHC uses 400 megahertz single cell on copper cavities, and also the Hadron Collider FCC-ee plans to use this type of cavity. And the 800 megahertz 5-cell bulk niobium cavity prototype has been built by JLab already 2 years ago and tested successfully. Okay, I have 0 left. Anyway, we also have magnets. We want very efficient magnets. We have novel magnets with 2 aperture magnets, where we have a single coil powering the 2 apertures, and we have a very good efficiency. We have 25 megawatt at TT bar, much lower energy at others, and we have prototypes both for the twin aperture dipole and for the twin aperture quadrupole. And we have first field measurements from these prototypes. And we have an arc vacuum chamber which goes with these prototype magnets. It's similar to, we have an antechamber which helps us to deal with the synchronization. We have photon stops inside the antechamber in discrete locations and in the vicinity of a vacuum pumping dome. We have to fight with some instabilities. Microwave instability and resistive wall is a concern, so this gets worse with neck coating. So for FCC-ee, we developed a novel, very ultra-thin neck coating with 100 nanometer thickness. This has been tested and qualified, has been published, and I think this will benefit many other machines, also synchrotron radiation light sources. A thesis has been published recently which summarizes all the collective effects. So if you have more questions, you can look into this Arias monograph, just published. Power consumption of the order of 300 megawatt for all modes of operation, slightly higher at the TT bar. If we figure of merits for lepton collider, if you take luminosity versus power, we see that the FCC-ee is the best machine up to the TT bar threshold, with much more than factor 100 better than other machines at low energy. And we see also electricity costs for present prices. We pay about 200 euros per Higgs boson. We think it's not too much. And if we normalize to construction costs, then for the construction, it's about 10,000 Swiss francs per Higgs in terms of construction costs. And it's 10,000 Swiss francs for 5 million Zs. And this is the total number of Zs produced in the entire lab program. So 10,000 Swiss francs for lab is not a bad deal. And I'm almost done. Option to further boost the performance. I think we could accept a shorter beam lifetime, especially with a more powerful injector. We could accept a shorter beam lifetime and push up the luminosity. We are looking at 4 interaction points, and we are studying scenarios. Beam coherent instability becomes worse with 4 IPs, but we have a solution. And also dynamic aperture is being improved with 4 IPs. We are almost at the level of 2 IPs. So in principle, this could be an option. And there are several presentations about this on Wednesday. And also recently, there is a proposal to upgrade EE using energy recovery LINAC technology. And it would look like this. It's similar to the old EREC proposal. We can accelerate. We excite over 8 turns. We collide and decelerate and recover the energy. The advantage is you get a much smaller beam, and then we get and we recover both the energy and the positrons for the next cycle. So it's 100% ecological. So that could be, and the performance. There will be a talk actually on tomorrow morning, just before lunch. The last talk in the SRF session, we put in this talk by Maria Camiso, who will present this proposal from Brookhaven. This is quite interesting. If you look at luminosity versus energy, here I have now FCC baseline is this dark blue curve. Here are the other proposed CPC, ILC, click upgrade, IC, etc. If you go to 4 IPs, we go to this dash curve here. We get almost a factor of 2. If we go to this energy recovery linear proposal, we get a factor 100 or more, and we also can go in energy above 500 GeV. So they call it, our colleagues in Brookhaven call this the bent ILC. And we need a 100-kilometer tunnel to do it. So this is quite exciting. So conclusion, we use many lessons. We have excellent performance at the moment. The technology exists. And we try to make the machine as power saving and as energy efficient as possible. And we have ultimate upgrade potentials. We can go to the energy recovery linear option, and we can go to the 100 TeV hadron collider after building the EE. We have several sessions. Tomorrow afternoon, Wednesday morning, it's very hot topics fitting for the temperature. And then also on Wednesday, we continue with the injector session and a machine detector interface. Okay, so I'll leave you with the 2 citations that I showed also at CERN recently. Bert Richter said in 1976, a plus and minus searching with a few 100 GeV center of mass can be built with present technology. So there seems to be no doubt that we have the technology. And he also told us that 100 kilometer is 100 kilometer is the best circumference for 360 GeV center of mass. You can see it in his paper. And Gus Voss told us that, of course, it should be the size of, not the size of an accelerator, but its cost, which must be minimized. And we are trying to do justice. So thank you very much for your attention.
Thank you, Frank, for having illustrated the economical advantages on the cost of the single links. So, questions?
So, come back to this ERL proposal. Is there some sort of a cost idea for this? And is this something that is vaguely envisageable, or is this completely crazy? Because it's too good to be true.
I think it's not completely crazy. It's more, maybe it needs some more studies. Maybe we need a test facility. It was the original ERIC proposal. And I think for DOE it was deemed too risky. That's why they went back to a storage ring option in Brookhaven. But for the Z and W, there is no advantage. The advantage comes only from the Higgs onwards. We have more time maybe to study this. I think the cost, I think, is negligible. The question is the feasibility, perhaps.
Okay, let's get the cost
Other questions?
The question of the 4 IPs. So now you said you think you have solution for that. In a recent discussion with Michael, I got the impression that it's a rather challenging problem after all. So what is the truth?
I think the geometry is challenging. It seems the beam dynamics now is almost okay, but to make a geometry which is compatible with the Hadron Collider could be more challenging, and also we need to cross. The beams always have to collide coming from the inside. So if we want to do that 4 times at 4 IPs, we need to bring the beam back 4 times. So we need another 4 kind of crossing points where we bring the beams back. So that we have 8 such places around the machine instead of 4. So, and then make it compatible with the Hadron machine is maybe more difficult. I imagine that might be easier at the Z and W. Maybe up to the Higgs. If we don't want, maybe if we accept 2 IPs at the TT bar and only ask for 4 IPs at the other energies, might be easier, because for the other energies, the synchronous radiation constraints are not so severe. Probably we can make shorter final focus and easier crossing. I don't know if that's acceptable. Do we want the 4 IPs for all energies?
Okay.
But it seems there's no beam dynamics absolute obstacle in the way. It's more a compatibility issue and a geometry issue. Also, wherever we have this IP, we need a wider tunnel, which increases the cost of the tunnel.
Okay, I suggest we thank the speaker again as we switch to the next presentation.
Good afternoon. Can you hear me okay? All right. I want to thank the organizers for giving me the opportunity to give this overview of the R&D on superconducting RF and power sources. And this presentation is given on behalf, of course, of the whole FCC-ee work package collaboration. So I'm going to try to not mess it up. Whoops. There we go. So you've heard this morning and this afternoon that the CDR books have been published. 3 of them are actually containing some of the SRF schemes for the different machines for FCC. In March, I believe, there was an update of the European strategy for particle physics in Granada, Spain. And I think the word of the decade is efficiency, efficiency, efficiency in terms of energy, superconducting RF and power sources. So I won't spend too much time because you've heard about some summaries this morning and this afternoon about the different schemes of SRF for FCC. You have basically 3 RF cavity sets for all options, some niobium on copper with single cells and 5 cells at 400 megahertz, as well as some 800 megahertz cavities, 5 cells. I'm sorry, the 400 megahertz are 4 cells. The 800 megahertz are 5 cells, and they are based on bulk niobium in order to ensure that you reach the correct gradient. Mm-hmm. All right, so in terms of efficiency, there is quite a bit of focus that is given to the optimization of the damping of the higher modes on the different machines. For example, for FCC-ee, there are various damping schemes that are explored for the Z options, and they are compared to the power that propagated in the couplers and the impedance of the cavities. There are different types of probes of HOM couplers that are tried, the hook type, the probe type, and also the double quarter wave type. For most of them, everything is okay in the longitudinal mode, maybe marginal and the transversal, except for the QW that needs a little bit more work. And you will hear all about it with Shanam Gorzikzadeh tomorrow morning in the SRF session. Same thing for FCC-ee. There is also quite a bit of work that is done in order to simulate the damping of these HOMs. And it's found that the threshold is actually lower at injection energy than in physics. However, for the wide open waveguide crab cavities that we will talk more about in a minute, the damping of the HOM has to be revisited. And Ivan will tell you all about it also tomorrow. The last aspect for HOM optimization is for the 400 megahertz cavities. And there are also here in tops of the hook and the probe type HOM couplers, there are two additional designs that are being simulated, a high-pass filter coupler and a bandstop filter coupler that are described over here. And they have been, all four types have been tested on 400 megahertz cavity and will be presented tomorrow by Niels Petri from Goethe University. So this was for the HOM part. Now, of course, you also have to optimize the surface of the cavities in order to minimize the losses and be able to reach the maximum gradient that is possible. There will be no presentation on this at this conference, but I just wanted to give a shout out to the group at CERN that's been working for several years now in order to develop the bulk niobium technology. At CERN, they have a successful development of vertical electropolishing, which is actually so far a unique system in the world. A lot of institutions have tried to implement it with so-so results, and they've been able to actually get to very good results past October. For bulk niobium cavity, they also have they have also done some development for high-pressure water rinsing, and I'm sorry, this is a mistake. This is high-pressure water rinsing, not two cabinets of electropolishing. You heard Frank just mentioning the development that was done at JLab on 800 megahertz bulk niobium cavities, where we have a single cell and a 5-cell cavity that was produced. The results were very encouraging. It goes beyond the specification for FCC. This is the curve for the 5 cells. And basically here is the regime requirement for LHCC, Pearl, and FCC-ee. There were also 2 cavities that were produced in order to allow the team at CERN to develop some thin film coating on that frequency. And an additional cavity, copper cavity, that was made in order to be able to perform R&D bench measurements in order to stack on cells. And the residual resistance is actually pretty good. So in the order of 3 to 4 nanoohm, and this is taking into account the 2.5 nanoohm due to non-conducting RF losses in the stainless steel flanges. So the single cell cavity is currently at Fermilab. It has been rebaselined, and it's waiting to be nitrogen doped. And they're going to use a recipe of 2-0 doping. So for those that are not familiar to it, it means that it's going to be exposed to 2 milliliter of nitrogen in the furnace for a certain amount of time, and then cooled down to room temperature. These are done at 800 C or 900 C, depending on the material. And this is followed by a 7 micron EP. And it's been seen that for most of the frequencies, you actually get an enhancement of the Q factor for this type of processing. That's actually the technology that's being used for LCLS2 that's being built right now at Fermilab and at JLab. So moving on to the niobium on copper technology, there is further development over the past year for the wide open waveguide cavity, which is a cavity that you can see Over here you can see the cross-section. The first prototype had been delivered by FCC last year. But there's been a lot of work that is being done in order to understand how this item is going to be coded. You actually have some mock-ups of the section of the complex that has been made in order to study the configuration for the deposition. And this is a critical location right here, because that's what you have the highest dissipated power. So it's a very nice structure, complicated. It's actually quite big. Nothing that surprising at CERN anyway, especially after the high isolder cavity at 100 megahertz. But the team has actually come up with a very clever way of approaching the sputtering in this cavity. In order to have a uniform coverage, they're actually planning on having 5 magnetrons in the cavity to code it. You have a mock-up of the system right here, and where the magnetrons will be at. And Fabio Avino, in collaboration with Almond Sibre, have done some try-up on one of the sections. Here you can see one of the first sample mock-up, and the region of interest where you want to make sure that you have good coding is right here. You can see the sample in the system, and the sample that is covered after deposition of 6 minutes. So they have a very nice thick coating after just 6 minutes, and of course it's only partially covered because there's only 1 magnetron in the chamber. So in the development for the wow cavity, actually there's another very elegant idea that has been developed in the past year, which is to manipulate the HiPIMS configuration in order to achieve higher ion energy during the deposition and thus get denser films. So the idea is to actually superpose a pulse of 50 volts during the discharge, and what that results into is basically the equivalent of applying a bias of minus 50 volts to your plasma, and this is very nice because you've seen the structure that I showed you. It's a difficult structure to actually bias. To apply, it's going to be something that's complicated. So if they can actually manipulate the magnetron, it's all gain. And they have seen that they actually get very nice results. They have a very dense film. They have less columnar growth, less shadowing. So that's a very nice results, and it's very encouraging. And this is basically a brand new technology in HiPIMS. And Fabio won't be here this week, but he published a very nice paper in Plasma Sources Science and Technology earlier this year, and it will be at the Superconducting RF conference next week in Dresden. So following with the niobium on copper technology, and the exploration of HiPIMS, so this is a technology that's been explored at CERN for a few years. It's also explored since less long at JLab. The advantage of HiPIMS, of high power, I keep on saying HiPIMS, but maybe I should spell out what it is high power impulse magnetron sputtering. It's based on magnetron sputtering, but because you have so short pulses, you actually get very high energy, and you're able to increase the energy of your ions that are produced during the deposition. You have here the system that is currently at CERN. The two systems are quite different. Here at JLab, you have 16 magnetrons that are stacked up in the cathode, but they give similar results, dense films, nicely polycrystalline. There is no, and the cavities results are very encouraging on both sides, in both institutions. Here you have a baseline for niobium. We're not quite yet at the level of the quality factor for the 1.5 gigahertz that were done at CERN. They were going to 10 to the 11, 10 to the 12, but we'll get there. One thing that you can notice is we do not have that strong Q slope that was so characteristic of the sputtered cavities, both for LEP and for the post-development in the years 2000. So that's very encouraging. In the same, one of the issues that both groups are facing is the substrate quality. And I'll talk more about that later on, and also the substrate preparation. In this case, I believe that actually at GLab for sure, and at CERN, I think for most of them, these films were coated on a chemically etched substrate, Subu, which is known to actually create some kind of an orange peel aspect on the substrate, and is not as favorable, for example, as an electropolished surface. So Marco Arzeo will give some updates on this, the CERN results, and I'll give an update on the GLab results. Now, we continue also development of GLab with energy condensation. Later on, some time ago this year, we actually found out another way of manipulating the structure of the film. So these two films were coated together in the same chamber at different energies for the nucleation, and then we played with sequencing of the subsequent growth, playing with the ion energy, also the thermal dynamics of the system. One thing that I would like to note, on this graph, you have the quadruple resonator sample RF measurement results that have been done, that have been coded at CERN and at GLab with ECR and HiPIMS. And I would like for you to pay attention to this result right here, where you have here a HiPIMS film that actually is behaving better at 2.5K and 400 megahertz than a bulk niobium sample. So this is very encouraging. Here you have you have the same measurements, but done at 4.5K. You don't have the same mitigation as of the Q slope, but we're still lower than bulk niobium and still much better than sputtered films. So you'll hear more about it from Marco tomorrow as well. Another development in niobium copper technology that is continuing, and that was introduced last year from the group of INF&LNL and the RS collaboration, is to actually overcome the Q slope by depositing very thick films. So typical films that we talk about at CERN or elsewhere, it's 1.5 to 2 microns in thickness. These films are 70 micron in thickness. So they were able to actually overcome the problem of delamination and stress that can build up in the film when you're doing sputtering. But they also changed the structure by pulsing the discharge with an on-off scheme, and you go to something that is very fine-grained and columnar to grains that are much wider in size. And you actually get, come on, really? You actually get some mitigation also of the Q slope, but this is ongoing. They also have developed a way to look at flux penetration in the cavity measurements. And Reza Valizadeh will present some of the material characterization for these films tomorrow, and Vanessa Garcia has also a poster tomorrow afternoon that will go more in detail with the RF measurements for these cavities. So these are on 6 gigahertz cavities, so cavities are about this big. But they are elliptical cavities. So as you heard, there's quite a bit of RF measurement that's done on sample, and the quadrive resonator cavity that was initiated 20, 30 years ago at CERN is now a twin that is supposed to be better, and has just been commissioned. Will work at the same type of frequencies, 400, 800, 1200, so they are very compatible with accelerator design. And you will hear tomorrow Marco mention that in his presentation, but you also have a poster from Dmitry Tikhonov from HDB tomorrow afternoon. Another characterization measurement technique that is being developed at CERN is actually a transition temperature cryotest stand that is being developed by Dorothea Fonescu. She has also a poster, no, she has a talk tomorrow morning. And she has been able to actually develop the test stand, commission it, and do measurements on niobium on copper and niobium on sapphire films. The A15, so looking beyond niobium on copper, if we wanted to really be efficient, as efficient as possible, is the development of A15 on niobium-3 tin for SRF application, and this is directly on copper, which is different than what can be done somewhere else, which is done on niobium. Earlier this year, Kate published a paper in the SUST, showing the different development they did for the characterization of the films. And if you remember last year, we said that there was a first QPR sample that had been coded. It was barely superconducting, but it was superconducting. Well, they made progress. They definitely got a superconducting sample where they were able to get RF measurements from. It has a pronounced Q slope, especially if you compare it to a niobium-3 tin on niobium QPR sample that was measured at HDB. It has a lower TC than on smaller samples, but this is normal in development. You typically go in stages. It's easier to have an homogeneous film on a 10 by 10 millimeter versus a 75 millimeter in diameter sample, but they were able to get a good RF measurement and a good quality film on a bigger surface. So this is still very promising. And for other material, so Marco, as I mentioned, we'll also talk about that since it's part of the QPR measurements. But there's also I just wanted to mention two posters tomorrow afternoon on SRF surfaces, which is niobium polishing from Berlina Chubukova from CERN, and also from Stuart Lees from Germany. That is the development of niobium nitride on copper. So as you may remember, what I mentioned a few slides ago is that we have an issue with substrates. People that may have heard me give me talks about films, you will always hear me say substrate, substrate, substrate. Substrate is key. If you do not have a good substrate, you have nothing. You can have the best film in the world, they won't be able to perform. So there's some efforts in the SRF community to actually develop better substrates. At Legnaro, they have taken over the spinning activity to produce seamless elliptical cavity, especially at 400 megahertz. There's quite a bit of work in the past 2 years that has been done. So this was in 2017, where they had the first seamless aluminum cavity prototype, also used as a mandrel. And they had to go through different types of annealing. They found out that they had to go actually not only to 2 annealings, but actually 3. And they were being able to complete the second spinning of the cavity. Now there are so the feasibility of the technology has been demonstrated. However, there are still a lot of development because there's issue with cracks in the surface. You have to have a better accuracy for the geometry. And the surface quality of the substrate. So they are doing some systematic studies. They also have some ideas in order to improve the technologies, to put it on an industrialization path, such as maybe instead of working from sheet, to work from extruded copper tubes, and use better machining tools to actually get to a net shape. A net shape structure. And this will be presented tomorrow by Christian Pira tomorrow morning at the SRF session. Now, as I just mentioned, cracks and spinning. So this is the type of surface you may end up with. At JLab, for example, we're using welding. So we deep draw the half cells, like it was actually done also for the 400 megahertz before, and they are E-beam welded. However, copper is a different beast than niobium. It's very finicky. It doesn't weld well if it's not extremely clean. So you have to, you actually have to take a lot of care. So there is a very interesting development that's ongoing at CERN. It was for another application. It was actually for net coatings, but it's to basically revisit electrodeposition of copper. And for this, you use a diamond cut aluminum mandrel, and you deposit your neck film and then your copper, and electroform the copper on top of that, and then you can dissolve the aluminum mandrel. And this was a development done by Lucia Amador at CERN, and she published a very nice paper earlier this year. So why can't we apply this to a cavity? And that's exactly the question that the group at CERN asked themselves. And this is under development, and this would be a way to actually have a truly seamless cavity, get rid of all the welds, because you could electroform your copper on top of already brazed conflat flanges. You would not have any material deformation. You can maintain very tight mechanical tolerance. So this is a very promising activity, and they got the first results in terms of the triple R of the OFE copper. They actually reach the standards for OFE copper, and they are expecting their first prototype for the summer of this year. And Guillaume Rosard will give you more information about that tomorrow as well. So the work is continuing on electrohydraulic forming, looking at the structure of the film with EM and ABSD, and Jean-François Croteau will give an update about this tomorrow. Now, moving on from the SRF surfaces and to the cryo modules, there's quite a bit of effort that also being done by Anton Ivanov into looking into the active shielding for cryo module by using a saddle coil seen over here. And this seems to be a very effective method. You can have a very homogeneous field that can be reached, and you can minimize the Earth's magnetic field. So it's very efficient, and Anton will talk about that more tomorrow. Now, in terms of RF power sources, so there's a couple of years ago, there was a development of a new Klystron bunching technology with increased efficiency, which is called oscillation method, also known as COM, and I'm sure that you are now very familiar with it. And Igor and Jinchi are actually continuing to use the Clysi simulation code in order to optimize the design for these structures and have them as efficient as possible and increase the efficiency as much as possible. A few percent are critical in terms of economy in the application of the operation of a machine. The similar developments are being done with at Thales for the higher efficiency classroom for the LHC. And this is a presentation that will be given by Armel Bonnat tomorrow, where he's also looking at different codes in order to simulate this better bunching. And they just had actually a workshop on energy efficient RF last week in Sweden. So the last thing is also the development of high-power IoTs, and there was 2 successful IoT technologies demonstrators that had been implemented And they are putting 10 guns in a circle, and the cavity is outfitted with 10 separate interaction gaps and simple outputs. And they had very good results. They were able to deliver, each IoT system were able to deliver 1.2 megawatts. These test beds are actually now at CERN for testing, and they have very, very nice results. And these IoTs are definitely not structures to be underestimated. They may be a little bit more expensive, but they could be very, very useful and efficient for some applications. And you will hear also tomorrow from Maria Yatas about the energy recovery LINAC option for FCC-ee. And at this point, there is no showstopper, but since I'm out of time, I'm going to let her tell you all about it tomorrow. And it will be some, a very interesting design to add to the FCC schemes. So this brings me to maybe a conclusion. So you can see that the R&D program for superconducting RF, as well as high power sources, are robust R&D programs. The developments in this framework within FCC will benefit all the schemes of the different machines that are envisioned in FCC, and also the machines beyond. A lot of these development can be applied for different, for different machines and different configuration. And we have also very active collaborations in the R&D in this work package. You can see here just an example of the past year, some of the specialized workshop that have taken place for LHC, thin film applications. I'm losing it right now, but excuse me. And the efficiency of the machines with the clusters and the IoTs. And that will be it for this. I think I'll say thank you. Merci.
Thank you very much for this very comprehensive review. We have time for just one question. If not, we thank the speaker again. Thank you very much. I ask the next speaker.
This one here, they'll switch and left, right.
Okay, thanks. So good afternoon, ladies and gentlemen. Thank you for the occasion to deliver this overview speech on infrastructure and implementation, and credits to my many colleagues. This year's selection on a vast field is highlighted here. You won't see anything from 2018. I refer here to a presentation at Amsterdam. This year we have 3 parallel sessions on Thursday and Wednesday. The whole will be summarized by Johannes Gutleber on Friday, and let's not forget the poster session tomorrow. More in detail, the list of oral presentations. We have 1 full session on cryogenics, 1 on implementation aspects, which includes civil engineering and administrative procedures, and then 1 on safety and technical infrastructure. And as we go through the talk, you will see the blue info boxes at the bottom, which refer to all these presentations and which I won't cite all explicitly. Just a little look back. Since 14 months ago, we had first contributed to the CDR in the first half, and then The people were a lot busy as well, together with on these activities in the long shutdown, working on the High-Lumi project and preparing for a smooth and productive Run 3. And we are all eager to know the result of the European strategy upgrade. But nonetheless, the field is very active, even if there are not always dedicated presentations to all the topics. Now, FCC is not only about technical matters, but there are also many challenges in the administrative framework. The more so because we are at the border between two countries. In France, we have one interlocutor, there is the French state. In Switzerland, we have already two, the Confederation and the Canton. So there are challenges on the institutional side, on the environmental side, on the time frame, but we can say that the main administrative tasks have been identified. There is a lot of work until 2025, and I think we want to be able to be trusted, have an anticipation of things. We cannot wait until everything is frozen and then put something on the table, but we have to cooperate all the way in this preparational phase with the host states, and we want to be exemplary in the environmental and legal aspects and also be as much as possible accepted in the local area. Now, there is a lot of activities going on. Public projects need to involve all stakeholders in an early phase, achieve a public acceptance, and all this costs a significant amount of time, but this will be paid off in the end when the implementation phase might then be based on a broad public support. This follows the subsidiary principle, which is valid in both host states. And here you see a little list of things we are actively pursuing with the two host states. Here we work with the Secretariat Rhône-Alpes-Auvergne, with CERIMA C2, and on the Swiss side we have a standing consultation structure, developed already a number of administrative scenarios and working also with external consultants. We have also a quite detailed timetable of these works. This is partly involving France, Switzerland, but also transnational activities. To point out here that the proper sequencing of the activities is crucial, and there are a lot of interdependencies as well, and everything needs to be well integrated. So at some time, pretty soon, one needs to set up a preparatory phase project and a team to deal with all this, with the fixed things and with the still open things. We have also had already a number of reviews for the CDR baseline footprint, let's say. We are continuing that. We have shown that we have a working solution, but we have to see whether we have better solutions, and also in the administrative processes at some moment we have to be able to show not only one working solution, which is the only one, but also a choice such that later on a choice can be made on all the aspects. Just to recapitulate very briefly the footprint constraints and criteria without going to details. There are urbanistic and environmental ones, machine design and performance and topography, and also man-made constraints, and some of them, they are interrelated, of course. Now, this you have seen in the past, the tunnel optimization tool, which was used up to now quite successfully, let's say, but this is more civil engineering oriented. It has strong points. It has all the geological layers as well as known and various other things. But if one wants to open the footprint exploration a bit more again and vary also other parameters which might be necessary, then this use is quite time and manpower intensive because it involves a lot of people, and such it involves quite a number of days to get new results, and if you want a lot of these results, it's quite cumbersome. That's why I wrote a JavaScript, let's say front end, a couple of 100 lines to that using OpenStreetMap, which then shows the footprint on the surface as one varies these parameters in real time. How that works, I show you briefly in here. Let's only look at a few points here, and this is all intentionally blurred and intentionally also made low resolution. So you see, for instance, if you want to move this point somewhere else, let's say on the CERN side, then you can shift here these points, the coordinates. Then you are on the ISR, let's say, where you find some space which can be reattributed. But then suddenly you find that this point is in front of the Geneva airport runway, which is not so great. Then you have to extend, for instance, the short arcs by a few photocells, and then you might still swing it a little bit around. And of course, everything like here is calculated in real time and is quite useful. So one can even enhance that by 3D or optimize that automatically. So civil engineering is, since Amsterdam, was busy with the CDR, finishing the high energy studies, spoil management, also these positioning questions, of course, from the CE side, and a lot of ongoing work. There's a schedule for the preparatory phase, meaning the next 5-6 years. Here, 3 blocks: site investigation, consultancy contracts, and construction contracts for start of construction 2029, with some advanced site preparation already in the second half of 2027. And what the site investigations are listed here. There are 3 different phases foreseen. A word about the geological uncertainty. There are areas which are better known around the ring from boreholes and from other projects. There are those which are a bit less well known, and then those which are, one can say, not very well known at all. How they are distributed and what the features and risks are there is listed here. Now, coming to the reuse of spoil material, you see a bit the structure as you go through the earth from top to bottom. There's moraine, typically, then molasse layer, which can be anything from sandstone to marls. And then there's a limestone as well in certain areas. Now I'm looking particular to this molasse reuse. There's a PhD study going on, what one can do with it, and that is very amazing that there are really some good new ideas coming up. What could be done with this? Also here one is working with bodies in the region, in Geneva and in France. Now coming to the geodesy, a topic which has never been presented here to great detail yet. This team has worked out, superimposed here on the general plan shown by Michael this morning, the backward planning, let's say, for preparation for all the geodetic aspects. The take-home message here is there's a lot of work. It is doable, but there's no time to be lost, actually. Same is true for the alignment and position monitoring. Here's a click design, which is at the moment, let's say, the proposed solution, but one knows that one can and should probably scale it a bit down, because first of all, it is used not in the linear tunnel, but in the circular tunnel here. The requirements in FCC-ee will be somewhat lower than in click, and also for the cost aspects. And then we will have also some more details to look at in the integration and accessibility around these 2 machines, the main ring and the booster ring. Again, here is a planning which is superimposed, and to reiterate, it will be a lot of work and resources needed also for this team. Integration, we have looked more in detail in the EE aspects, because there we had to catch up a little bit. Here you see a stretch of dipoles and quadrupoles on a girder. The interconnect, the idea presently for that, the synchrotron radiation absorbers, integrated vacuum valves, and some of the alignment system. Cryogenics has a full session, as I said. I don't go too much into detail here. There are the 2 engineering studies for the large plants, which will be reported on. That is a special study also to complete HH for the inner triplet magnets, which has been, let's say, evoked at the last conference. And there are also 4 fellowships going on in the Easy Train program, which will also partly be reported on at this conference. cooling and ventilation, they're looking into several aspects, integration of the air inlet and air extraction, also the water distribution, the EE design as already shown in the previous slide or 2 slides ago, cost model, further RF ventilation, which will be quite demanding in the points where the RF is, and environmental impacts, where do we get the raw water from, how do we distribute it, where do we reject used water, and heat recovery possibilities, and also the question how to maintain the cooling system over 3 years, 4 years, when we want to have longer accelerator runs. Powering, that is, there are various facets as well. People are working on the power converter design with several criteria on the quality of the power with a good, not perturbed supply of power from the grid to the sensitive loads, and also safety aspects. This was a study done by Thomas Höhn recently and shown at this conference, and found quite some interest in how to integrate medium voltage DC grids into the power distribution, which could not only be applied to particle accelerators, but also in the larger industrial production processes where sensitive loads are. This is being at the moment evaluated, and one is looking how to integrate that into the overall powering scheme. Now, final one on powering is that could be a layout of a supply at one point, and there are various areas here in blue and green. First of all, where can one put sensibly energy storage, where would one profit from? And also this is a question, and how the loads can be connected to the grid and to the main supply. Transport has already had a master concept at the last conference for logistics and transport, actually, and they made a small study this time on how to transport larger amounts of personnel, for instance, during the installation, but also maintenance periods from the surface or from one point to the next with a sensible speed. Then safety, we have half a session on that. There was a safety study in the CDR has shown that we can deal with life safety objectives. Then this should be complemented in the future, looking a bit to the future into the fire safety studies, some details of compartmentalization, fire and rescue service, and so on. Then one slide on the HE ventilation study, which has also been complemented, has complemented the other studies for the HH and EE, which we did already. So this is now also done. Then further studies shall be railed up for cryogenic safety as well. Several points are mentioned here. And finally, also in radiation protection, there are some topics going on and planned for, which shall come then in the next phase. R2E, they have updated the beam screen layout, which led to a slightly different and using a different residual gas profile, coming to different deposition or heat load deposition in the coils here is slightly higher than before, but less absorbed, of course, on the beam screen, 5% of the power loss as opposed to 16%. Then the impact on electronics, let's assume the electronics would be placed underneath, or some would have to be placed there. Also here one sees a slight increase, in green the previous one, in blue the new values. And finally, the availability studies for FCC-ee. You know that we had it already for HH last time. Now they are applying the same methods, one can say, coarsely, which are described in a generic way here. Also to the EE study aim is to look where the new technologies are used, where the complexity scales up, and where known technology is used in a different environment. And that, knowing that generally EE colliders have a good availability track record. Now they're using as input the operational scenarios, experience from other machines, the layout of the injector complex, The critical systems, mainly RF, magnets, electrical distribution, energy storage, and a question of operational efficiency. How often do you fill? How long do you fill? How many injections might be rejected, etc. And then there are some preliminary indications that redundancy in key systems can help, and they want to identify and document risks and solutions to be able to focus the future R&D. That brings me to the conclusions. The I/O Infrastructure and Operation Working Group is active and motivated despite being involved in many other activities. The CDR contributions have been delivered, being qualified as adequate for the current project stage, and I take this occasion to thank all my many colleagues for their great contributions. So far, we have not seen showstoppers. The work is ongoing and much more is planned to consolidate, iterate, and deepen certain areas. At the moment, the main focus has to be on optimizing the footprint, getting these administrative processes mainly railed up, and also doing the planning for certain important preparatory works, which might still take quite a while before one can do any groundbreaking, namely geodesy, for instance, alignment studies, site investigations, etc. So much intensive work is to come during the next phase, and we are all looking forward to news from the strategy upgrade. Thank you very much for your attention.
Thank you very much. Thanks. Questions on infrastructure?
I had a question when you mentioned the operation of the accelerator over 3 or 4 years.
Yes.
The FCC-ee is supposed to turn off, have a shutdown every year.
Yes.
So what is the meaning of this operation for 3 or 4 years?
I don't know exactly how long it will be, that shutdown, whether it is sufficient to service everything, what is then running the injector complex, the main rings, and so on. And I think it's also a bit of projection into the future. It was not only on EE then.
Right, that's more for the Hadron Collider.
There was also that, yes.
Thank you.
Mm-hmm.
Other questions? I had a curiosity on this new scheme of protecting from voltage dip. Which kind of, what would be the duration of these voltage dips?
What would be the?
Duration, the strength of the voltage dip in...
The voltage dips, I think it's, okay, there can be perturbations on the network from lightning strikes, from other problems on the more lines will in the future lead to all these various points, and there are like cryogenics, motors, and so on. They can be sensitive to these kind of things. I don't know typically how big they are. There was a plot in the Amsterdam which showed the dip depths to the length, but also another thing, we are not only looking at the short dips, but there are also, so to say, the longer dips during the ramp up and ramp down. These should be covered then with by local storage. So there is a part really the short term, let's say 100 milliseconds or something like that, and there are the longer ones over 10 minutes where one has a really high power consumption, but which in the end will go down. So this could be fed in from batteries or from other systems, and then when you ramp down, you feed it back into the storage system.
And this will regard anyhow the low tension sector, the 1 to 3 kilovolt
yeah, that
network.
It depends on the, let's say, implementation where you do that and on your load. I mean, typically, for instance, in cryogenics, you have 3 kilovolt loads. You can think of having at a higher voltage. I'm not a power expert, let's say. That could be at a higher voltage level and a medium and probably at a low one as well.
Thank you very much. So, other questions? Not, I think we have to thank all the speakers again. Quite surprisingly, we have 4 minutes ahead of schedule, so we have coffee break up to 4.